Hello everyone, my name is Bhupesh Kumar. I am currently working as a researcher at University of St. Andrews. I would like to sincerely thank the conference organizer for the opportunity to present my work. Today I will be discussing our work on tunable random laser based on solid state polymer system. Here is the outline of my talk. First, I will briefly introduce the concept of random laser, highlighting how they differ from conventional lasers. Next, I will focus on challenges of achieving single mode spectral emission in random laser and how we address mode selection in disorder system. Following that, I will present recent progress on tunable random laser, and then I will dive deep into our results on single mode spectral tuning, showing how we can combine selective pumping with thermal tuning to achieve precise control over emission. Finally, I will summarize our finding and future direction of this work in the conclusion section. So what is random laser and how it is different from the conventional laser? Conventional laser consists of two parallel mirrors placed around the gain medium. One mirror is fully reflective while other is partially reflective to allow the laser beam to exit. Light waves in such lasers, light waves are reflected back and forth between the mirror and causing constructive interference, and only specific wavelengths that satisfy the resonance conditions are allowed to laze. On the other hand, random laser, there are no traditional optical cavity like conventional laser. There are lots of randomly distributed scatter in the gain medium. When such a medium is optically pumped with a suitable light source, multiple scattering of the light increases the path length of the light in the gain medium and provide necessary feedback for amplification and lasing. So random laser are kind of optical system where feedback come from multiple scattering instead of well-defined optical cavity. So bottom right shows a typical multi-mode random laser spectrum where multiple mode lays together, unlike conventional laser which is a monochromatic source of light. The experiment that truly ignited the interest in random laser was conducted by a researcher at Northwestern University in 1999. They pumped zinc oxide semiconductor powder, which is a gain medium that emits in the ultraviolet range, and observed a narrowing of the emission spectrum followed by emergence of sub-nanometric spectral lines similar to those seen in conventional laser. Remarkably, this takes place without the presence of well-defined optical cavity, which raises critical questions about the origin of lasing modes and the nature of the feedback mechanism. The explanation of this lies in the phenomena of Anderson localization, where the presence of strong disorder light wave becomes spatially confined due to multiple scattering, and these trapped modes act like a mini cavities within the disorder system. Despite the randomness, certain light path results in constructive interference, forming a closed-loop trajectories that provide necessary feedback. This allowed coherent light to build up and amplify within the localized regime, leading to random lasing even in the absence of traditional optical resonators. Since then, random lasing has been demonstrated in various disorder systems. The same research group at Northwestern University also developed a microscale random laser, presenting an elegant solution to the challenges of creating highly reflective mirrors at small length scale. A notable 2D experiment using zinc oxide, a popular material due to its UV emission where uh, the mirror fabrication is difficult, highlight the potential of mirrorless random laser in UV regime. Researchers continue into the gain mechanism and demonstrated random lasing in cold atom gases. Additionally, random lasing has been demonstrated in opals and photonic crystal structure infiltrated with dye molecules. In the photonic crystal community, interest has surged as researchers recognize the role of structural disorder. Since achieving a perfect crystal is practically impossible, leveraging the inevitable residual disorder has become a promising strategy to enable or enhance lasing behavior. Further, random lasing has also been demonstrated in optofluidic random system. Random lasing has also been demonstrated in various biological systems or biocompatible system. Here is the example of random lasing in bacterial cellulose membrane, which are doped with rhodamine dye 6G or with silicon or silica nanoparticles. The high porosity of this biocompatible material allow efficient embedding of the scatter and enable optical feedback. These bacterial cellulose can be used for biomedical application like artificial vessel or wound dressings. Random lasing has also been demonstrated on a paper which make a case of a low cost flexible random laser using a soft lithography. These lasers produce a very narrow emission line from a localized scattering modes, each with a very unique spectral code that is very ideal for secure tagging. Let's say for n such materials or n such lasers, up to 2 raised to power n unique markers can be read and using a single laser pulse that is useful for tagging. This can be used for tagging currency, document and ID cards. And further, the random lasing has also been demonstrated in a DNA matrix where DCM dye is doped with the DNA dope inside a DNA matrix to avoid fluorescence quenching, and that also improved the heat dissipation. So DNA lipid complex with the dyes and scatterer enabled fret tuned random lasing, which shows the potential of bio-based lasing material. Further, random lasing has also been demonstrated in human tissue that has been used to distinguish between cancerous and healthy tissue. Doped with rhodamine dye 6G based on their different emission spectrum, it was able to figure out which one is a cancerous and which one is a healthy tissue. We have designed and fabricated our own custom disorder structure embedded with gain medium to study random lasing phenomena. The passive host polymer was PMMA, polymethyl methacrylate, with a molecular weight of 49500, doped with a 5% weight of laser DCM dye. A uniform layer of approximately 600 nanometer thickness was deposited by spin coating the doped solution at 1000 rpm for 60 seconds, followed by a post baking at 120 degrees Celsius for 2 hours to evaporate solvent and ensure solid and stable film. To fabricate 1D disorder structure, we use E-beam lithography to carve 62 randomly distributed parallel grooves into a PMMA DCM layer. Each groove was 200 nanometer wide and 50 micrometer long, spanning a total length of 500 micron. That means the all 62 grooves are distributed over a length of 500 micron. The average spacing between the air groove was approximately 8 micron, which create a controlled disorder pattern suitable for studying random lasing behavior. This is the optical microscope image of the whole disorder system, and this is the zoom in high resolution SCM image of the few air grooves. When disorder structure was optically pumped using a laser strip from a frequency doubled ND arc laser, which is a picosecond laser and emitting at 532 nanometer. When the dimensions of the pump exactly matches the sample size, this produced and the lasing and there is enough power to overcome the losses. This produced a sharp lasing peaks over a weak spontaneous emission background. This is something that has been demonstrated in various random lasers as I discussed in previous slides. Here you can see that there are multiple modes here. But the real challenge is, can a random laser emit monochromatic light like a conventional laser? In the coming slides, I will show we have achieved the single mode lasing by applying feedback based iterative pump optimization method and successfully suppressing the multi-mode emission and achieving a single mode operation. To achieve single mode random lasing, we adopt a method where we shape the pump profile to selectively excite a specific mode. This is accomplished by using a spatial light modulator that is controlled by a computer generated images to modulate the pump beam before that is projected onto the sample. Here pump beam is split into 32 grayscale coded blocks. Each block can be scaled on 256 different levels and displayed on the SLM. Since this pump profile is not known for a given to select a given mode, the pump profile is not known. So we adopt here iterative model free optimization approach. Each time new spectrum is recorded and feedback to the algorithm. For pump shaping, We use a Nelder-Med simplex optimization algorithm implemented via fmin search function in the MATLAB. The goal of the algorithm is to enhance the target intensity of the target mode with respect to the next highest intensity of the mode. This method is particularly suitable for this task as it does not require gradient information, making it ideal for noisy, nonlinear and experimental driven system. The algorithm iteratively updates the simplex through reflection, expansion, contraction, or shrinking until conversion criteria is met. This approach is robust in real-time experimental conditions and effective for optimizing complex high-dimensional laser systems without requiring detailed system model. We have implemented this iterative optimization method on our sample, and for that we have used this experiment setup where spatial light modulator is used to modulate the incoming pump beam, and after modulation the pump is imaged on the surface of the sample from the bottom. We are using our sample is on a substrate of fused silica, which is a transparent one, so that allow us to pump the sample from the bottom and image it from the top. We have achieved single mode operation at any desired wavelength picked from the uniform pump emission spectrum. It took almost 200 iterations for one complete optimization, and algorithm converges to a non-uniform pump profile that optically promote the target mode lasing wavelength while suppressing other modes below threshold. Here we can see that 5 unique modulated pump profile for 5 different wavelengths selected individually. Why tunability is challenging in random lasing. The local variation in both the gain and scattering property often results in broad, unpredictable spectral output. This complicates selective tuning of the random laser. However, tunability is very important. It significantly broadens the scope of application for random laser, enabling their use in sensing, imaging, and spectroscopy. By tailoring the emission to specific needs, tunable random laser offer greater functionality and adaptability than fixed wavelength system. Tunable random lasing has been demonstrated in various systems. One of them is this polymer optical fiber. The temperature controlled spectral tuning in random lasing was demonstrated in optical fiber which are doped with dye and nanoparticles. The lasing arises here from multiple scattering within the fiber core, and due to high thermo-optic coefficient of the polymer, temperature changes tune the refractive index and causing a red shift in the lasing spectrum. Broad spectral coverage from visible to infrared has also of light has been demonstrated using gold nanostar suspended in dye solutions. These nanostars act as a broad scattering center and form randomly distributed resonators that supports coherent lasing modes. This type of system exhibit narrow emission line width below zero point 0.1 nanometer, confirming that gold nanostar provide highly efficient coherent feedback over a wide spectral range. Additionally, wedge-shaped random laser composed of disordered silver nanoparticle embedded in dye-doped polymer has been fabricated via press coating. Coherent feedback is enabled by both multiple scattering and plasmonic enhancement from the nanowire. By adjusting the excitation position along the thickness gradient of the wedge, the lasing wavelength can be tuned continuously from 560 to 580 nanometer due to reabsorption effect. The thicker region of the wedge support more lasing mode, enabling simultaneous multi-wavelength operation and mode selection, offering a simple yet very effective method for tuning random lasers. In another approach, a liquid crystal based planar random microcavity infiltrated with pneumatic liquid crystal has been developed and optically pumped. This structure emits highly directional and ultra narrow line width laser which corresponds to a Q factor of greater than 20,000. The lasing wavelength is thermally tunable by changing the temperature from like 27 to 35 degrees Celsius and shifting the emission spectrum from 605 to 608 nanometer, even though it's a very small bandwidth, but still it offers another solution to tunable random laser. As I have shown, we have already shown that single mode lasing is possible by iterative pump optimization, but it does not allow lasing at arbitrary wavelength, as emission is restricted to discrete lasing mode inherent to the multimode emission spectrum of the random laser. If we overcome this limitation, it will provide full spectral control of random laser. Here we explore thermal tuning as a method for controlled wavelength adjustment. The random laser sample was mounted on a copper plate with a rectangular aperture that allow pumping from the bottom, and the copper wire plate was thermally coupled to a heating probe for controlled temperature variation. Due to thermal induced changes in the refractive index of the polymer, we observed a blue shift in the lasing spectrum, as you can see in this figure, as the temperature is increased. Specifically for each 5-degree rise, it results in a 0.1 nanometer shift in the wavelength. Over a temperature range from 25 degrees Celsius to 75, that is starting from room temperature to 75 degrees Celsius, we achieved a total shift of 1 nanometer for each single mode individually selected. With this, we can tune any individually selected mode by 1 nanometer by just changing the temperature. Before going forward, for continuous tunability, we first confirm the spectral stability at higher temperature, and we performed measurement at a higher temperature at different time interval and found that for up to 45 minutes the spectral remains stable within plus minus zero point 0.1 nanometer. Now we move to continuous broadband tunability. Here piecewise spectral tunability over 8 nanometer by tuning 10 different lasing modes has been shown. To achieve this piecewise tunability through mode hopping, the disordered structure must support sufficient density of the mode. Specifically, to achieve a continuous tunability over a bandwidth of 8 to 10 nanometer, at least 10 to 15 modes within that bandwidth is required. Here we show that piecewise tunability over a bandwidth of 8 nanometer by selecting 8 to 10 different individual modes and tuning them using by hitting the sample. We also measure the directional emission of our random laser by measuring the angular distribution of the emitted light. For this we use a 20x microscope objective coupled to a multimode fiber that is connected to the spectrometer to record the spectrum intensity, and this microscope objective is scanned across the cross section of the laser. This collection system is placed at a 10 cm from the sample edge and aligned orthogonally to the sample to achieve to capture the emission along the lateral direction. From this measurement, we determined that approximately 50% of the total emission is confined within plus minus 2.5 degree of the central axis, indicating a relatively high degree of directionality. Here I will summarize the key achievement of our work on tunable random laser. First, we have achieved a single mode lasing by tailoring the pump beam profile using spatial light modulator. Next, we have demonstrated wavelength tunability through thermal control and observing a shift of 0.1 nanometer with every 5-degree rise in temperature, and achieved a total shift of 1 nanometer for each individually selected mode. Then we verify the spectral stability of each lasing mode at higher temperature and confirm that even at higher temperature at higher stable temperature the spectrum remains stable within plus minus zero point 0.1 nanometer over a much longer time. And for broader control, we explored piecewise mode hopping, showing the potential for multi-mode access by designing structure with densely spaced mode, about 10 to 15 lasing modes in 8 to 10 nanometer of continuous bandwidth operation. Finally, we have also addressed the directionality and find that 50% of the emission in our laser is confined within plus minus 2.5 degree. Thank you everyone for your attentions. If you have any question or query, please you can send me by the email that is given on the first slide. I will be very happy to answer.